controlled 6-pulse bridge rectifier. Now you get different variations. You get a half control. The uncontrolled, we have diodes in all 4 positions. The half control, we will have diodes for half of them and controlled devices for the others. I have now selected to do a fully controlled. And this one's name is really fully controlled 6-pulse bridge rectifier. You can see that once more we have the same numbering as with the diodes. So we automatically now know. First T1, 60 degrees later, T2, 60 degrees later, T3, 60 degrees later, T4, 60 degrees later, T5, 60 degrees later, T6, then back to 1. That order has been set out for us. This rectifier has got a problem. It's called the starting problem. And the reason it's called the starting problem is because when it starts, you must apply a pulse to one of the 3 devices that are on the negative side also. You have to supply the positive and the correct one at the negative. With diodes, it didn't matter. The moment that diode switched on, this diode became force biased and it conducted. After you have got rid of the starting problem, you only have to fire the next one that has to come on. Now, a thyristor works like this. Positive here, negative there, and then a positive with respect to gate, pulse there. Then current will flow through it. So it will not switch on if this is positive and negative and there is no pulse there. Then it stays off. Okay, so that is open switch. The moment I put a positive pulse there, then it closed. How does it open? To open it, must be negative on this side and positive on that side. And the current through it must have reduced to 0. So the current has had to go through 0, and at that point there it will be switched off. After the current has gone in a reverse direction. There, and removed all the carriers in the outer 2 layers and wait for the gate recovery of the inner 2 layers. Then this thing will be open. Okay. So usually it means you have to force the current to 0. Now, the time that we delay from a point where a diode would have switched on until this device is triggered is called the delay angle. Now let's see here. A diode would have switched on from V3 and then V1 would have become the most positive and then current would have flowed through that thyristor. Now let's delay for 30 degrees. Let's delay alpha there for 30 degrees. Then it means that the device that was on will stay on until I trigger that device. So the device that is on stays on until I trigger that device. Then the device connected to V1, that is T1, switches on and it conducts. And now it stays on, and when it reaches this point, if it was a diode, the next one, then it would have switched on, but it's not a diode. It is waiting for the pulse on its gate, and that pulse is delayed by 30 degrees. And only then does the device switch on. And now device T3 is on. At this stage, if this was a diode, we would have switched over to that device. But now it's not a diode, it's a thyristor, and it waits for us until we switch it on. And only then does it go over, and it comes down here. And now we delay with 30 degrees before we switch it on. So this red here is B positive. positive. Are you happy with that? Now, we go to the other side of the coin. The device that was on will stay on, and it will stay on until it receives the pulse. And the moment that it receives the pulse, it switches on, and now the supply over the load on the negative side takes that shape. Here a diode would have switched on, but there's no diode. So it stays on until we reach that point there, which is a 30-degree delay angle. Then it switches over to that phase, and now it stays on. Here a diode would have switched on, but now we wait for 30 degrees until it is switched on. And where does it go now? It goes to that point there, which is this point here. And there the whole process starts repeating itself. Now we have V positive and we have V negative. So this V negative here is now this color. If we now want to have V load, what we need is to subtract V negative from V positive, because that is what V load is equal to. So 0,866 minus 0,866 gives us 1,732. Now you are there. Then 0,5 minus V max gives us, or 0,5 minus 1 gives us 1,5. Are you happy with that one? Then 0 minus 0,866 gives us 0,866. Now here's a vertical change. And the moment there's a vertical change, we have to do this thing twice. 0,866 minus 0,866 gives us 1,732. 1 minus 0,5 gives us 1,5. 0,866 minus 0 gives us 0,866. 0,866 minus 0,866 gives us 1,732. And now there you have the pattern. And since you have the pattern, you can apply logic, and once you've applied logic, you just check and see if your logic was correct. And now all you have to do is join the dots so you can see the big picture. And there is V load. What do you notice about V load? Well, it's the limits from pi over 2 to 5 pi over 6. Do you agree? Of what? V load is V line max sin omega t between which limits? Pi over 2 and 5 pi over 6. So it will be this area. If I can determine that area there, over that period there, then I can determine what is VDC, what is the load voltage. Now let's turn our attention to the currents. IT1. Where does IT1 flow? IT1 flows from there to there. Do you agree? Okay. IT2. Do you agree? And that value there is IL, and that value there is IL. What can you say? Where do you think IT3 is going to be? It will be at the end of IT1, which will be in the middle of IT2. So there is IL. IT4, end of IT2, middle of IT3, IT5, and IT6.
Interval of 60 degrees.
120, and there's a 60 degrees interval between each one is 120 and 60 degrees after the next one starts. So here in this case, we'll start off there. How do we determine the RMS rating of the thyristor? IT RMS is equal to the root of the mean. There's 120, 120, 120. So we have got IL 0 and 0. So we have IL squared plus 0 squared plus 0 squared. So it's the root, the mean, there are three of them, the square. And that gives us IL over the square root of 3. Now, which rating must you choose? Because when alpha is equal to 0, the load current is going to be the highest. But I just wanted to show you that the formula is exactly the same. You must just go and say IT RMS, alpha is equal to 0, and determine what is that current then, before you determine the rating. So once more, I1 is equal to IT1 minus IT4. So IA is equal to I1 times the turns ratio. So once we've got that, IB is equal to I2 times the turns ratio. And when you get to IX is equal to IA minus IB. Just in exactly the same way as we did it before. And once more, you have to go and look at your minimum alpha. When is maximum current going to flow? Now the transformer rating is equal to the number of windings. Now if this is the secondary, number of secondary windings times V RMS of the secondary times I RMS of the secondary. And that is dependent on the wave shape. Okay, which we can get from there, which is this, in this case, this I1 RMS value. And if we look at the primary rating is equal to NP times V RMS. In this case, it will be the line voltage. Do you agree? Because it's a delta winding. V RMS. Okay. And I RMS. And I RMS will now be IA